let's get started. Welcome everyone to the second day of ISEC 2024. I am very happy to have Akash Lal as a keynote speaker with us today. Akash is a senior principal researcher at Microsoft Research India. He's an expert in the field of concurrent program testing, wherein not only he has contributed theoretical ideas, but also put those ideas into practice. Over the past several years, he has been working on a tool called Keynote that it's a tool for systematic testing of concurrent programs. And I know that a lot of work has gone into not just scale the tool for real world programs, but also to make it accessible to the programmers and users, which means that a lot of effort has gone into documentation, manuals, tutorials, and I think it's a critical factor in that the tool has been downloaded about 1 million times, and it's also extensively deployed in Azure for systematic testing of Azure cloud services. Akash has won several awards over his career, including his PhD thesis at University of Wisconsin-Madison, won the ACM Sick Plan Doctoral Dissertation Award. He has won several Best Papers Award in top-tier conferences. And last year, for his contribution to the field of concurrent program testing, he was a recipient of the CAV Award. Today, he is going to tell us about his journey through concurrent program testing and how he put his ideas into practice and into deployment, and looking forward to learning about it.
Okay. Thank you. Thanks, Asim. Thank you to the ISEC organizers for inviting me to give this talk here. So what I'm going to do is that, instead of describing the solutions and the tools that we have today, I'm instead going to, I'll introduce the problem of concurrency testing, but I'm going to rather focus on the journey through research that led us to the practice that we see today. And this is just to give an illustration or an example or perspective of how many of the things that we see around us are the result of decades of research by the research community. So a lot of the work I'm going to be presenting here is going to borrow heavily on the work done by my collaborators and sometimes even broadly in the research community. So a lot of this is, I'm taking the liberty of offering my perspective on the work that I've seen around me, not necessarily work that I've done myself. Okay, so what is concurrency testing? Let me just introduce that problem to you. So let's say you're a software engineer and you have just joined a company like Microsoft or Google or Amazon. And the first task that you're given is that you have to code up this data structure called a dictionary, right? A simple key value store, map keys to values. Okay, so you know C#, so you go about writing this piece of code. You write your dictionary. Dictionary has you have to support your methods like addition of keys, addition of key value pairs, whether a key is a member, removing a key, and so on, right? So, you're fairly confident, you write this piece of code, you go to your manager manager says, very good, but how do I know that this program is correct, right? How do I assess the quality of this code? So I say, okay, no problem, you go about writing a few test cases, right? So, it's a simple dictionary, so what you do is you create a dictionary, you call some operations on it, you write an assert, and now you make sure all your test cases pass, all right? So now you have good quality code, all right? So now you get promoted. So now you're, getting more senior in the company. So you're given a slightly harder task. So you have to write a concurrent data structure this time, right? A concurrent dictionary. So what that means is that this data structure should allow multiple threads to operate on the data structure concurrently, simultaneously, right? So it's more efficient that way. So you go about, doing the same thing that you did before. You create a concurrent dictionary and you define your methods. You look up your algorithms book and you code this up, right? But your manager comes back and says, okay, convince me that your code is correct. So now this is where the problem starts to come. How are you going to write good tests for this concurrent piece of code? Right? So if you go about doing the same thing that you did before, which is create a dictionary and call some operations on it and then have some assert, this is not good enough because it's only testing for sequential behaviors. It doesn't say what happens when multiple threads are concurrently going to access the data structure. All right, so these kind of test cases are going to miss things like race conditions. So there's a whole class of bugs that you've missed, and in fact, you've missed the whole point of having testing the quality of concurrency in your code. So this is the problem that we face today, right? This is very real, and a lot of people who write concurrent code face this, right? Are you going to write effective test cases for this piece of code? And the problem is because, so what do? You try to write a test with some concurrency in it, right? So this is how you would do it in C#. So instead of calling these methods one after the other, you just call them concurrently. But the problem with writing test cases like this is that you don't get any idea of the coverage that is going to happen when you run this code, when you actually run this test, right? It might happen that most of the times these tasks execute in a serial order and don't even exercise the concurrency, right? So in some sense, as a person testing this piece of code, the way it is getting tested is completely out of your hand. It depends on how the operating system is going to schedule these operations. Right, and for simple data structures, you will in fact see that most of the time the executions get serialized. Right, so the prevalent state of the art, if I am to say, is to do stress testing, where you take this idea, but instead of just calling 3 operations, maybe you will call thousands of operations, and then you just make sure your code doesn't crash, right? That's what people do today. But it's unsatisfactory because you're kind of, it's based against hope that by doing a large scale testing that you're exercising all kinds of behaviors. Becomes very hard to write assertions, and it's even harder to debug. So if something fails, what went wrong? It's very hard to be able to establish something like that. Okay, so that's what concurrency testing is about. Just slightly more formally, it's about given the fact that you're given a concurrent program, and you're given a test case, right? So something that exercises the program and has an assertion in it, right? Some specification of what the program must be able to achieve. And the problem is to know whether this test can fail, right? And if the test can fail, we provide a deterministic repro of that failure, right? And this is a state space exploration problem. Your concurrent program is defining a state space induced by all the ways in which the program can execute, and you have to explore that state space, find one that violates your specification. Okay, so illustrate that a little bit. What I'm showing you here is a simple program. You have 2 threads, thread 1, thread 2. Each of them are operating on 2 global variables x and y. So they're just doing some simple writes to x and y. Right, so now an execution of this program is basically going to be an interleaving of these operations, these 4 operations across the 2 threads, right? And this graph shows you, various different interleavings. So if you do all the green and then do all the red, you observe this set of values for x and y, and so on. You can have various different interleavings, right? That makes sense? So by the way, feel free to, I don't know what the protocol is, but feel free to interrupt if you have any questions. Yeah. Yeah, I just gave one example, but you imagine whenever your job is to write the concurrent data structure, right? You wrote concurrent dictionary, and now you have to write test cases that are going to exercise that piece of code. So naturally, you will write test cases that exercise it in a concurrent manner, right? So you have some concurrency going on in your program. So this is the problem is your state space is very large. So just generalizing from the same example, if you have n threads and each of the threads have length k, then the number of interleavings that are possible in this program is exponential in n and k, right? So this is a very large state space to explore. So this is what we're doing. Now I'm fast forwarding, after I motivated what the problem is, and I'm fast forwarding to the solutions that we have today. And how, what is the status of those solutions. So I have, along with my colleagues at Microsoft, we have created this tool called Coyote. So it is a .NET library, and for solving this problem of concurrency testing for C#, right? So the same example I showed you today, you had C# concurrent dictionary, you can write a test case, and those kind of test cases, you can just give it to Coyote, and it will do the state space exploration for you. So that is the problem it solves. It's available open source, and there is a lot of documentation and learning material available on the web. And it combines basically 2 key pieces of technology. So there is engineering on one side, So what you have to be able to do is you have to be able to understand concurrency in commercial languages like C#, these are very big languages, and there are lots of different ways in which you can do the same thing. So a lot of engineering goes into understanding concurrency in C# and taking control of the scheduling so that you can reliably control interleavings, right? So that is one piece of work that goes into building this tool. And the other is actually the algorithms, the search algorithms that are able to explore these state spaces effectively. Okay, so now we've been working on this for a number of years, and this is, so what we do is we gather a little bit of telemetry. So anytime someone downloads and uses Coyote, we get some lightweight telemetry back, and this is an accumulation of that telemetry for the last month. So I took this snapshot yesterday. So in the last 30 days, what this says, this is the number of times a Coyote test has been invoked. So a concurrent test has been invoked using Coyote. And the total is around 300,000 for 30 days. So roughly 10,000 tests are running every day, exercising concurrency in some piece of code and using Coyote for exploring it. Right? And so, these are some other statistics. So on average, it's finding like 1,500 bugs every month. And the total amount of time spent in doing the state space exploration across all of these runs is about 20 million seconds. All right. So this is to impress the fact that this tool is there, people are using it, and a lot of people are using it. All right. But like I said, I'm not going to spend so much time on describing Coyote as it exists today. I think what is more important is to look at the journey and how we got here, right? So we're going to take a step back, right? And I think, so where is all of this work coming from? So broadly, even before concurrency testing was a thing, all of this state space exploration was really the domain of this field called model checking, right? And model checking also came from hardware verification. So the idea was that whatever system you're trying to analyze, you create a model of it, like an abstraction of it, and then you thoroughly exercise the entire state space of that model. So that's why it's called model checking. And this is really the only approach that you could apply to concurrent systems, right? But the problem there was these state spaces induced by concurrency get very big very soon. So insisting on doing a complete exploration of that state space was not very scalable, right? So that's where the challenge comes in. Now, in order to address that, the prevalent state of the art was to say, well, okay, I can't explore the entire thing, so I'm going to only explore a subset of the behaviors, right? And that's where this depth bounding came in. So people would build algorithms that would explore the state space up to a certain depth. And this depth is on the length of the execution of the program, right? So 10 steps, 15 steps, 20 steps, 100 steps. You fix a bound, and then you only explore up to that bound, right? This is a very simple idea, but unfortunately it didn't work very well because even though you could finish your exploration up to a certain small depth, it wasn't really finding you bugs. Right? So the problem with concurrency testing becomes the following. So you can't explore the entire state space. So you must pick a subset to explore, right? So in order to get scalability. So that's scalability on one side. Versus the tension is, you have to achieve scalability while also getting precision. So this subset should be good enough in order to find bugs, realistic bugs in programs, right? So that is what the question is for concurrency testing. And the solution that came about through several years of research was the following. The way you pick this subset is that you bound the number of context switches between threads, right? So instead of fixing a depth bound, what you fix is a context switch bound. Let me illustrate that using an example like this. So this is the same example as before. I have two threads. Each of them are length k. Then the total number of interleavings is exponential. But what you say is that I am only going to explore all executions with 3 context switches. Okay. So what this 3 context switches means is that you pick 3 places in 3 points in the execution of these threads, and you can only switch to the other thread at those points. Right. and you fix the number. So the bound you fix is the number of context switches. And as soon as you do that, what happens is that the exponential goes away, and in some sense it becomes a polynomial in n and k. All right. Yes. So I'll get into that a little bit. And so we do have ways of injecting, basically a scheduler in the operating system, in the runtime, in the language runtime. Sorry? It's not exactly transaction boundaries. The way you can understand it is that, see, by default, when you run a program, there is a scheduler that is running. The scheduler may be part of the language runtime, or it may be part of the operating system that is actually deciding when to switch between threads. So you basically take control away from it. You say, okay, I'm not going to rely on the operating system scheduler. Instead, I'm going to have my own scheduler. And you interpose that into the language runtime. So you take control of the scheduling in that way. I'll talk about it a little bit, yes.
So, there is a distinction between context bounding and preemption bounding. So this is like you're talking context bounding.
Yeah, because I went back in time, right? So this is like, early days, and I have enough gray hair to kind of like go back in time, really long time. So that's where it started. It started with context bounding, and then this idea got refined. You will see that I will say that eventually the solution you see today is not exactly context bounding. It's some variations of those ideas, but this is where it started. Sorry, I couldn't hear you. So you don't decide which points. All you decide is the number of context switches. So I will say 3 context switches, right? And now your job is to explore all executions with at most 3, right? You explore all of them with 3 context switches. Yes. So the programmer. So you have to write a test case. So imagine that you're writing a test case, and the test case has an assert. You fail the assert, you have bug. Yes.
So what is the intuition behind this bounding of context switches? Why are we confident that this is effective in finding bugs?
I will get to it. If I don't get to it in a few slides, then you can remind me. But I think that that's going to be the point of this talk. All right. So this is the time when this work happened. Kind of luckily, I was a grad student while this work was happening, so I was observing it very closely. But the idea kind of got introduced. So I will talk through these 4 papers. So this is a timeline. Starting at 2004, plotting when certain papers got published. I will talk about these 4 papers as I move along. But collectively, these define the idea of context bounding, answering this question that it is basically, so for any kind of bounding metric, you must answer 2 questions. The fact that you can do efficient exploration within that bound. And the second is that it finds bugs, lots of bugs, right? So you have to be able to answer both questions, and that evidence came through a series of these 4 papers. And once the problem got defined, and these papers showed the evidence that you can in fact solve both these things that I just mentioned, and then the community picked up. So after that, there were lots of papers that got published. I stopped tracking after 2012. But a lot of papers got published on extending the idea and applying it to various different domains, various different kinds of concurrency, various different kinds of programming models, programming languages, different kinds of bugs, different notion of bounding, and so on, right? So it's this research machinery that got kicked in, and a lot of what we see today is a result of all of this work that has happened. Okay, now we go back in time, right? So this is early 2000, before the first paper got published in 2004. So there, at that time, the dominant methodology for doing program analysis was to do verification, right? Take a program, build an abstraction of it, and just verify it for correctness, right? So, the theme was, let's verify our program instead of saying, let's find some bugs in our program. Okay, and one of the tools that was very influential at this point in time was this tool called SLAM. Some of you may have heard of it. So it was a tool for doing software verification. So it would be able to, it would consume the source code of Windows device drivers. So it was built for analyzing device drivers, but only sequential behaviors of device drivers. And it followed this methodology that it built an abstraction and did model checking, and in order to verify correctness of device drivers. So at this point in time, this paper was very influential and won several awards by itself also. All right. So now, my colleagues working at that time, they knew the potential in SLAM, and it was getting all this attention from everybody on how good SLAM was at analyzing device drivers, but it wasn't doing anything for concurrency. So the first, I think, step taken in this direction of concurrency testing was this idea. Let's find some bugs at least, right? We have to do, we have to analyze concurrent programs. Can't do it fully. We can't verify them. We can't explore their entire state space. That's okay. Let's leave all that aside. Let's just find some bugs. All right. So the methodology they proposed is the following. So they said we're going to take a concurrent program and we're somehow going to rewrite it into a sequential program. And once I can do that, now I'm going to use the same tool. That's very efficient tool. I'm going to use the same thing, and I'm going to do analysis of the concurrent program, right? And this transformation, the way they designed this instrumentation, was for 2 context switches. So they did a program transformation that worked for only 2 context switches, right? And let me show you how that works. So in this program, let's say I have to do 2 context switches, one at this point and another at this point. The way you can do it is the following. So I can rewrite my program, and that instead of assuming concurrency between the 2, I'm just going to assume that this is a sequential program that starts execution here. And at the time when I have to do a context switch, the way you simulate it is that you have a non-deterministic jump. You just call the second thread. It's a procedure call. Okay, so you call this. So what's going to happen is that when you call this, your thread starts executing. And at some point in time, whenever you want to do your second context switch, you do a return, right? And when you do your return, your control is going to come back here, and this is going to execute. All right. So do you buy the claim that this is simulating 2 context switches, right? And this is a sequential program now, right? So there are lots of non-deterministic branches, but it's a sequential program. There are calls and returns. That's all that's happening. There's no concurrency there. Okay, so you can do this transformation. Now, feed it to a sequential analysis tool, and then if it comes back and says there are bugs in your program, you know that there is a concurrent bug in your original program.
So the second context switch is randomized, but the first one is fixed.
No, first is also randomized. I didn't show it. Oops. So you imagine that this if star is also everywhere here. Yeah. And the actual transformation is a little bit of generalization to this. But you see that this only works for 2 context switches. You can't make it work for more than 2. Because what is happening is that when you do this return, this procedure just goes away, right? And now when you come back here, you can't just say, oh, resume from where you left off, right? That's not how procedure calls return, right? Very simple idea, right? And, that's what this paper was about, just this slide. But also showing that it actually worked in practice. So just, it's a simple idea. They were able to find lots of bugs. So they found lots of concurrency bugs in real code. They found race condition in device drivers. This is, there are other benefits to this technique as well, and it scaled fairly nicely. But the coverage was inherently limited, right? It was a simple experiment in some sense. Surely 2 is not going to be enough for finding all kinds of bugs.
So what happens to the local state? Because if you return then...
It's gone, right? So you can't come back. So that's why you can't do more than 2.
So they don't link it to a local state?
No, nothing. The transformation is pretty much what I showed on that slide. Yes. Yes. Yeah. So yes. So I was not very precise. So this way, basically, you can only call it once. If you've called it, then you can't call it again, right? So this if star will be everywhere, but at most 1 call to that thread, and you can't make another one. Yeah. Yeah, good question. Okay, all right. So, this was some evidence, right? This is not really solving concurrency testing, in general, but it showed evidence. It gave us perspective that finding bugs is cool and interesting, which was lacking at that time. But it also raised curiosity of people is that, can we take this approach and generalize it further? And so it was in 2005 when this idea of context bounding was introduced. So this general problem of doing context bounded analysis was that you're given a concurrent program P, a positive integer K, and you have to answer whether P can go wrong with an execution with at most K context switches. All right, so they introduced this problem, but they did not follow the same methodology as before. Instead, this problem was kind of hard and difficult, so they decided to pursue just giving a decidability result for it. Okay, now, so what happens is that if you have, so one way to explain why the analysis of concurrent programs is so complicated is the fact that even if you take Boolean abstractions of your program, like very simple abstractions, analysis of sequential programs is, efficient, but the analysis of concurrent programs becomes undecidable, right? So even in simple abstractions, the analysis quickly becomes undecidable. So the question they posed is that, okay, what if instead of general concurrency, we have only K-bounded concurrency? Then, what do we get a decidability result there? So this paper offered that result. So they just showed that under a Boolean abstraction, the analysis is decidable. Right? And the way the analysis worked is that it was actually a construction. It was a proof by construction, where they showed that you can compute the entire state space of that program. The state space is still infinite, but you can capture that state space in using a finite state machine, right? And then there's an inductive argument that if your set of states is finite state machine, then in one context you can only get to a set of states that is also captured by some finite state machine, and that you set up that inductive argument, and that's how you get your decidability. Yeah, Raghavan.
So this is for programs and not just one thread, is it? Not just it's not just one sequence of instructions, but a looping program.
Yes. Yeah.
Okay, because I thought the K-bounded was for like two given threads. Just straight line.
No. You imagine that these are programs, right? The straight line is for illustration, but.
Okay, because straight line is obviously decidable, right? Like with K-bound.
Straight line is decidable.
Because it's fixed, just two fixed sequences of
instructions. So this K-bounded is for
general programs.
Programs, yes. So push down abstractions of programs. All right?
Akash, just
Yes.
quickly here. So in the context in which this work was situated, so the chess kind of a model checker, did it assume the executions to be terminating? I assume it did, right?
Yes.
Which means it was considering loop-free programs.
Yeah, so, okay, so what I have done, so I haven't gotten, in my journey, I haven't gotten to chess yet, so it doesn't exist at this point in time. But to answer your question, so the way, Raghavan's question is also well-founded. The reason for that is that I'm switching between static analysis and dynamic analysis. Right, so in static analysis, the problem is you're doing analysis of the source code, in which case Raghavan's questions apply. So then you're dealing with programs that may have loops, non-termination. You're dealing with source code of programs. So this work is static analysis. The one I showed before for two context switches, that is also static analysis. But when I show these straight line programs, they basically come from dynamic analysis, where you're dealing with programs that you run and execute. So in those cases, you assume that it's a finite length executions, and your programs are essentially straight line because you're doing dynamic analysis. Does that make sense?
This decidability is for static analysis.
Yes.
Of general programs.
Yes. Push down abstractions of programs. Okay. All right. So, this is a decidability result, right? So it doesn't really say how you build tools. It wasn't even efficient. I don't think anybody implements this algorithm directly. But it left with these questions. Everyone in the research community was kind of, their interest was piqued by these results. But these two questions still remain unanswered. Does k greater than 2, does more than 2 context switches really matter? Are we really going to find more bugs if we increase the number of context switches? And the second question was that this decidability result, can we translate it to an efficient implementation that we can try out and use? All right. So, this is where I picked up and added a result to this series of results. And this is to answer the second question, whether you can efficiently implement this context-bounded reachability. So the way the analysis worked is actually we went back to the idea of doing this program transformation. And this kind of transformation that takes a concurrent program, does some source code transformation and spits out a sequential program, that's now called a sequentialization, right? There's a general term given to it. And the way it works is that it takes this concurrent program, P, context-bound K, and it outputs a sequential program, P sub K, that preserves reachability under K, right? And now you can do your same sequential analysis on P sub K, and you get your answers on the concurrent program P. Yeah.
So by sequential program, you don't mean one single sequence of instructions, but non-multi-threaded program.
Yes.
It's still a program.
Yes, it's a program, yes. I'll make it more precise. Maybe I will not make it more precise in this talk, but give me that freedom for now, and we'll take the other questions offline. Okay, and this is a linear time construction. It was very simple construction. All you do is rewrite your source code, and you get a sequential program, and now you can kind of do sequential analysis on it, right? Okay, so this showed that this kind of context-bounded analysis was efficiently implementable. Now, let me just describe a little bit of where this idea came from, and how I got into working on this problem. And for that, I think I'm going to ask ask for your forgiveness in advance, because I'm going to show you some math without really explaining what that math is, right? So just bear with me for a little bit. So this idea actually comes from this. We were doing weighted. I was doing in my PhD thesis, I was doing weighted reachability. All right, so reachability is like imagine you have a graph. Reachability just asks the question whether there's a source node, target node, is there a path between them? That is reachability. But if you start doing things like weighted graphs and you do shortest path, so that's like weighted reachability, right? You want to know not just the fact that there's a path, but what is the weight of that path. Okay. Now this weighted. So what this means is that every edge is going to have a weight. In our cases, these weights were matrices. Okay, where these matrices came from, just ignore that for the time being. And the way, like in shortest path, you add weights as you go along. But in this case, what you have to do is you multiply the weights as you go along, right? So you do matrix multiplication. So if you have a path like this, if you have a path, the weight of this path is the multiplication of the weights of the individual weights of the individual edges. So the weight of this entire path is this matrix multiplication. Okay? All right. But now the problem we're going to do is we were solving weighted reachability on concurrent programs. So not just weighted reachability on sequential programs, we could solve, and that is the problem that I was working on in my thesis. And we said, okay, there is this algorithm that shows the decidability of k-bounded reachability. Can we show the same result for weighted reachability? So in this case, what happens is that the edges gets colored, right? So the color represents a thread, right? So there's a red thread and a green thread, and there is interleaving between them. And you have to do weighted reachability in this kind of a graph. Okay? The way we did it is the following. So the problem with concurrency is this interleaving is very hard to manage. Knowing when to switch from red to green and vice versa, that becomes very complicated. So we came up with the technique that will avoid this interleaving, right, which is what we call reordering. So instead of doing this, what we're going to do is we're going to do the entire red first, and then only do the green, right? Somehow similar to the original idea for two context switches, right? You do an analysis of a thread, finish it, and then only go to your next thread. But how are we going to do this, right? So how are we, from this sequence, how are we going to compute a weight of this sequence? So the idea actually came from matrix algebra. Right, and this was, completely unanticipated. We, just stumbled upon it by accident. But let me explain to you how it worked. So there is a different way you can multiply matrices, and it's called a tensor product. So the tensor product of two matrices, A and B, is this big matrix where you have pairwise products of every element, right? So you all 4 elements here, all 4 elements here, gives rise to 16 elements here, pairwise product of every individual elements, all right? Doesn't matter what it is. What matters is this equation. This equation comes from matrix algebra, right? This is well known. I think if you go look up Wikipedia for tensor product, you will see this thing, being highlighted in the first few things about tensor products. So what it says is the following. It says if I take the tensor product of A1, A2, multiply it with the tensor product of B1, B2, then what I get is A1, B1, A2, B2. Okay? Now at this point in time, what you have to do is you have to kind of imagine all the symbols go away, right? Forget what symbols mean. Just read the order of operations. What this is saying is here the way the A and the B read is A1, B1, A2, B2. This is an interleaving of the A's and B's. If you read it here, there is no interleaving, right? So you have all the A's here, all the B's here, right? So this equation basically told us that there is a way of computing an interleaved product using a sequential product, right? And so this is the idea that we applied for solving weighted reachability. There's a little bit of other math that needs to fall into place, but because I'm running behind in time, I'm going to skip this part and just ask you to trust me that this math, the way this math works out. So if you have two threads, this one is doing M1, M2, M3, M4. This one is N1, N2, N4, and you want to do an interleaving between them. So you want to do an interleaving, full interleaving between these two threads. Then the way you can do it is that you compute a tensor product of M1 to M4, compute a tensor product of N1 to N4, and then you can put it together and you can get an interleaved product. All right? So we took this idea of weighted reachability and we applied it, and that's how, simplifying it, you got to the sequentialization that you can just do these kind of things at the source level. Okay? Good question. So these weights are actually abstractions. Okay, so you can think of a weight as a transformation on the global state of your program. Okay, so the weight is a transformation, and the composition, the multiplication of weights is actually the composition of translation. So what we are actually doing is that we are tracking changes to the global state of the program through these matrices. And I can explain more to you offline if you want. Okay, but the first question is still there. Does it really matter?
It's a transfer function.
Yes, yes. Yes. Okay, so now we were equipped with this ways of actually trying this out. So we tried it out. So we did this experiment. The experiment was the following. So we took a benchmark of concurrent programs, and on the one side we applied a tool called SMB, which was kind of like the state-of-the-art tool at that time, which would do full exploration of that concurrent program. Okay? Versus we applied our analysis called CBA, context bounded analysis, and we fixed the number of context switches. Okay? And what we found two things. We found that all the bugs that happened in those benchmarks, they happened in 6 context switches or fewer. Okay? This is the first thing we found. So a lot of bugs you can find in a small number of context switches. That is important. The second thing is that if you optimize for it, if you only search up to depth of 7, we were about 30 times faster than the state of the art. Right? So it gives you efficiency and precision both at the same time. All right. So now, this is work in the context of static analysis, right? So there was this discussion about, static versus dynamic. So at the same time we were doing this static analysis, there were, other group of people, in Microsoft that were doing dynamic analysis, right? So the difference between the two is the following. So there are 2 ways in which you can analyze a program, right? One is that you can read the source code and figure out what it's trying to do. The other way is that you can compile it and you can run it, right? So dynamic analysis is when the only thing you do is that you're prepared to run the program. That's all. You don't look at the source code. So they built a tool called Chess, which was very influential at its time. So they were doing dynamic analysis. So there the idea is that given a concurrent program, the only thing you can do is you can run it, but you're going to run it repeatedly and every time explore a different leaving up to k context switches. So they built this tool that was able to do this exploration, and they showed the following results. So let me actually read out what this graph means. So what they did is that because you're doing this dynamic analysis, of essentially finite state programs, you could cover the entire state space of that program, right? So that is the 100% here. So every line is a different program, right? Think of every line as a different concurrent program. And this plot says that how much of the states would you cover if you only explored executions up to a certain context bound, right? So for example, if for this program in 2 context switches, you could do 80% of the entire state space of that program. No, so there is no baseline here. So this is percentage of the state space that you cover, right? So you do the full exploration, right? You will get, okay, this program has 1 million states. Okay, and now what you do is now you do context bounded exploration. You say explore all states up to 2 context switches. Turns out that you can, it induced 80% of the entire state space.
Sorry, I missed it. Was it in the static setting or the dynamic setting?
This is dynamic.
But then it's also dependent on the input, right? Because
Yeah, so it's fixed. It's fixed input, yeah. It's like a fixed test. So that's why the state space is fixed, finite state space. Okay? So, by being able to cover all executions up to a certain context bound, you were getting, a fair amount of behaviors of the concurrent program, which is why the earlier graph I showed is that a lot of the bugs were happening in a few number of context switches, right? So this all kind of tied in together nicely. Okay, so the other thing, the other contribution, which is to the question that was asked earlier, is the fact that you can design these systems efficiently. So what you have to be, the way programs normally execute is that you have your compiled program, it runs on their language runtime or your operating system. Now changing either of these is a hard thing to do. But they showed a technique where you just need to interpose on the interaction between the program and the runtime. And if you can do that, fairly well, then you can take control of the concurrency in the program, right? So you have an interception mechanism that all on concurrency and synchronization APIs, you get control of the program, and now that was sufficient to take over the scheduling of the program, right? So they showed that the effective ways of building tools like this and how you can control concurrency. Okay, and this So that was the set of 4 papers that I talked about earlier, right? So these papers together, they defined, a new approach to the same problem. They said, okay, let's, if bug finding is interesting, then this context bounding analysis is very useful. It showed how you can do static analysis through this program transformation. It showed how you can do dynamic analysis by building efficient tools that essentially work on unmodified concurrent programs. All right. Now, all of this work is interesting, but interest is, not enough, right, for industrial use case. You also need a compelling argument showing effectiveness in practice. And that, I think, happened roughly on, in this piece of work. So, so what happened here is that, the Windows USB stack, so USB stack is, imagine it to be like a file, it's a kernel module, so like a giant device driver that controls the interaction between the operating system and your USB device, okay? So the Microsoft team, they were redesigning the architecture of this device driver, upgrading from 2.0 to 3.0 architecture, right? So it was a complete redesign of that concurrent system. And they anticipated that concurrency testing is going to be very important for them. And so they started applying the kind of techniques that I mentioned earlier. And so they used this concurrency testing all throughout the life cycle of that design. So this 3.0 stack is running on all Windows systems. I think maybe Now it may be later versions of that driver, but at that time it was an upgrade on all Windows machines. And they found that the concurrency issues that they were hitting were insignificant. And a lot of that came through all the testing that they put in while they were doing development of this system. It led to a better design. It, in fact, even led to faster performance. So because they were encouraged by the testing that they were able to do, the team was able to apply much more sophisticated concurrency patterns than they would do otherwise, and that those patterns gave them better performance as well. So a lot of this experience is captured in that paper.
Was there any, so this paper applied the ideas that you talked about on this problem and showed that
Yes. Yes. Yeah. Yeah. It didn't use chess. It used a variant of chess called Zing, which was a similar kind of a tool. But yeah, it applied. The concurrency testing was all based on this idea of context bounding. Also that, yes. So there are other aspects that come into this, but the analysis was Zing, and Zing was doing this bounded exploration of concurrency behaviors. Yes. Yes, chess, right. It is a, I'm trying to remember. Yes. Not in production, yes. You only need for testing, yes. That's right. That's right. Yeah, so I don't remember the exact technology they were using, but it was some kind of rerouting mechanism. So whenever you call an OS system call, you redirect to your stub. All right, so this showed evidence that these ideas are real, and then when applied in practice, make a difference to your business, right? So you need these kind of evidence to actually, get better adoption in the industry. So Coyote, the tool that we built was, accumulation of a lot of these ideas, right? Including the system design, including the algorithms, and even absorbing a lot of the work that happening in academia on different kinds of newer variations of context bounding that were coming up. And Coyote actually found a home not in Windows but in Azure. So at the same time we were designing Coyote, the role of Azure inside Microsoft was going up, right? It was, the cloud business in Microsoft was growing and growing very rapidly. And as a result of that, a lot of people were building, infrastructure for Azure. So Azure is the cloud infrastructure, right? And a lot of the infrastructure is concurrent and distributed, right? So there were lots of concurrency issues and a lot more developers who were facing this issue. So that is what drove the adoption of Coyote, and is being used today in many parts, in almost all parts of Azure. Right, and this kind of usage is what is driving the graphs that I showed earlier on the usage statistics. Test NG. I don't know about that one. Okay, like I mentioned a few times that the algorithms that we implement today actually are not context bounding. That idea is kind of been refined over several iterations, and people have been able to come up with more efficient state space exploration techniques, all based on the encouragement that context bounding works. So the ones that we use today mostly are based on randomized search. So there are slight different variations, but they give you this probabilistic guarantees of finding bugs rather than for doing full state exploration, and so they're more efficient. All right, that's mostly what I wanted to cover in this talk, right? So if we look back, what we saw is a lot of interplay between research and practice, right? The tools that we build today don't come out of just sitting and thinking and then coming up with the entire solution in one go. They take years, in many cases, even decades of work to go between very theoretical decidability kind of results to very practical system implementations, and it's usually the interplay between them that was driving a lot of this work. What you also saw is actually dedication to the same problem over a number of years, where multiple people thought that this is an important and interesting problem. They saw that this is a very important problem to work on, and through various different kinds of approaches, finally arrived at solutions that actually work. Right? But that was looking back. So looking ahead, I would say by no means have we kind of solved this problem. If anything, there is even more of this problem to go around. Concurrent systems are getting more and more important than they were before. Through the cloud infrastructure and other kinds of systems. And what we need to be able to do is not just focus on the testing part of it. Right? The testing, in some sense, comes very late. A lot of what software developers do is actually, the process of writing software. So what we must be able to do is that take inspiration from the way we do testing and validation, and then have more abstractions in the design process itself that will help people build these software in a manner that are easier to test and validate. So a lot of that work needs to happen, and there is not enough of it happening today. So with that, I'll stop here and take any further questions if you have.
So we can take a few questions.
Unit test for testing concurrent application is not easy, right? Any work around maybe recommending writing unit test or generating unit test for concurrent?
Yes, it is not easy. And in fact, is one thing, if I were to summarize the experience that we've seen with Coyote being used in Azure, a lot of teams are using it. The part that people struggle most with is writing these specifications and test cases of being able to capture what exactly is correct behavior in my program. So what do they do? So in cases when you're confused, what you do is you try to make your specifications simple. That instead of coming up with a general specification that works in all kinds of scenarios, what you try to do is you focus on one particular test case. Right? If I were to call my system with a GET request and a PUT request, what are the kinds of behaviors that I can possibly see? I can see behavior 1, 2, or 3, and that's how you go about writing your specification. Right? That's the procedure most people follow. Whether there is something you can do more broadly, more generally, I'm not sure. But yeah, that's an interesting space to look at. Yeah. So so the place where Coyote is used today is in Azure services. So these are like distributed systems.
Akash here, Sujit here. Have there been efforts in overlaying traditional model checking ideas like partial order reduction or DPOR on top of context bounding?
Yes. Yeah. The short answer is yes. A lot of people have used it. We don't use in Coyote. I think so we move more towards doing this randomized search. Okay, we find that to be much more efficient at finding bugs. But the trouble with randomized testing is that it is not that effective in showing the absence of bugs, which is what you want when you say, oh, my program is correct, right? So there, partial order reduction helps.
So most of the talk here and most of the research is also on concurrent programs is on exploring the interleaving space. Mm-hmm. But then there is also the input space. So like what does Coyote do for exploring the input space?
No, so it doesn't do anything. So that is still the responsibility of the programmer.
I see. Okay.
This was very interesting, obviously a complex research-intensive domain. So my question would be, do you see some generative AI approaches to explore this research domain itself, meaning applying AI for new concepts in this domain?
That is a good question. I think one place where there's a possible match is actually tying back to the question earlier of writing specifications. So I think that's one place where generative AI can help. So, so for example, still today in software engineering, when you write a piece of code, its intended behavior would actually be documented in natural language, through some form of documentation and learning material and so forth, rather than documenting it in logic. It's because people, find natural language more useful than they find logic. So bridging that connection between how you can take documentation, consume it, and produce, formal specifications. If you can do that, then you can unlock, one part of the story, and then you have, once you have a specification, now you can start doing formal validation. So I think there is some potential there. Yeah, possibly there's more to explore also.
Hi Akash, thanks for this interesting talk. My question was towards the last part of your talk. You spoke about randomized testing with probabilistic guarantees and learning-based techniques for the state-based explosion. Both of these techniques you have worked on. I just wanted to get a sense from you, in your experience, which of these two seem to be at the forefront? I mean, working on them would give more benefits.
These two, when you say two, one is
The
randomized.
learning-based scheduling techniques.
Sorry?
The learning-based.
Learning-based,
Yeah.
okay, yeah, okay. I think, so the advantage of this randomized testing, I think is because it's very easy to implement, right? You need very little machinery in your system in order to be able to do this randomized testing. I think that is why it is so heavily used today. Because part of the problem is that you have to engineer these systems. These systems have to be able to understand all the ways in which you can do concurrency in your program, all the ways in which you can do synchronization, and there's a lot of work that needs to happen in order to do this engineering exercise. So the simpler the algorithms, the simpler the engineering, and that's why they get used a lot more. With learning-based techniques, in places where we are able to do it, we see benefits of using those techniques, but they also impose a little bit more burden on the engineering itself. Actually, that's also the reason why partial order reduction isn't used that much, at least in our systems, is because it's just harder to implement. You need a lot more information from the system in order to be able to do partial order reduction.
Akash, here.
Sure.
Okay. Akash, I was wondering again, we have so many systems already, right, that are not built with concurrency in mind. So are there efforts, or what is the progress in this in this particular area in terms of automatically or semi-automatically going towards concurrent systems?
I would say, there are research efforts in that direction. More practically, people have looked at things like software transactional memory and other hardware-based solutions. But in terms of anything I see being used in the industry, I'm not sure.
Actually, I was more curious on the industry side, because this is a serious problem from industry side too. In terms of the effort that would be required. So any large scale, or do you see that there is need for some large scale efforts on trying to see, let's say an organization has 1,000 software projects, right? And maybe out of them maybe 10% of them may fit for concurrency, and how do we do that transition?
I'm sure the problem is there, right? The problem is definitely there. Your machines have more and more concurrency in them. You have multi-cores and so on. So you have to be able to exploit that concurrency. But I am not aware of any systematic exploration of doing this translation. The most of what I see is just rewriting.
Okay.
You rewrite the software.
Thanks.
Yeah, I think this K-bound, what you told, context switches, right? If you do randomize, is it ad hocly done, or there is some gray box thing coming over there? Because, practical programs will be large.
Yes.
Okay, and then K, where those K, right? You might have just touched the surface of the things, actually. Okay.
Yeah.
So then, to identify those right places at which randomization to introduce, do you do some gray box analysis of your program and then do it?
No. It's very simple. you just predict the length of your program, and then your K points are chosen uniformly at random within that bound. It's a very, very simple algorithm, but very, very effective. Maybe the part of the reason it's so effective is because the state of concurrency testing, without using these techniques is not that great. So maybe that's why a lot of these techniques are that useful. But yes, I think you need more research in topics, in questions like this in order to be able to do even better. Thank you. Thank you.
So it's my pleasure to announce the Best Paper Award. So on behalf of of Asim and myself and the program committee, I would like to announce that the paper Code Queries, a data set of semantic queries over code, is getting the Best Paper Award. The actual award will be given later today, but we wanted to announce it in case some people leave. There are 6 authors of this paper: Surya Prakash Sahu, Madhurima Mandal, Shikhar Bharadwaj, Aditya Kanade, Petros Maniaris, and Shri Shrivare. Thank you.